So today we're going to talk about something called directed acyclic graphs. So these come up a lot. So I'm going to write down the definition, and then we'll talk a little bit about where these might come up and why we care about them. So write it way over here. Definition: a directed acyclic graph, which is abbreviated DAG, D-A-G, for directed acyclic graph. And people really honestly say DAG. I mean, they'll pronounce it that way. This is much shorter than saying directed acyclic graph. So it's what it sounds like. Is a directed graph with no directed cycles. Okay, and I say no directed cycles to emphasize that we care about our cycles where you're following the edges and you get back to where you started. If there's a cycle of edges, but they kind of go different directions, that's okay. So so this is, so like you can't have this, right? That's no. But if you have something like this, like this is still okay, right? It kind of looks like a cycle, but it's not a directed cycle because you can't go all the way around following the edges in the direction that they point. So why do we care about these? So directed graphs come up when you're you're modeling things that have relationships with direction, and often when the relationship is some kind of less than relationship or some kind of ordering relationship, like this comes before this, then naturally you're not going to have any cycles. So some examples would be like, imagine the graph where the vertices are courses, say courses at Hendrix, and you draw an edge from one vertex to another if one course is a prerequisite for another, right? So this might be like algorithms, and this is 151, this is one, I don't know, whatever. I mean, right, so you have an edge. So obviously you're not going to have any cycles, because that would be ridiculous if you had like a bunch of courses that each required, like you could never take any of them because you wouldn't have the prerequisites, right? Another place that comes up would be like some kind of factory process, or where you're manufacturing something and there's like a bunch of steps that have to happen, and certain steps have to happen before other steps. But again, obviously there's not going to be a cycle because then you can never make anything. You have to kind of be able to get started with something. Or even like when you're compiling something, there's a bunch of files you have to compile, and you have to link them, you have to link in certain other libraries, and there's kind of certain things you have to do before other things, but again, there's not going to be any cycles. And so those analogies suggest something which turns out to be very important and related, which is whenever we have some things in a relationship like this, a directed acyclic graph, we often want to know kind of what order should I do things in so that I respect the prerequisites. For example, if I have all these manufacturing steps that need to happen, I might want to know, what order can I do things in on my assembly line so that I will always have already done the required things before I go on and do the next things. Or if you want to take a bunch of classes, let's say you can only take one class at once, right? What order should I take the classes in so that I'll always have the prerequisites before I get to the next class? So this is called a topological ordering. I will put it up here. A topological ordering, which is also called a we could call it a topological order, or a topological sort, or just a top sort. Right, so like kind of the most correct name, I suppose, would be a topological ordering. But usually, if you're talking about this with someone else, like another computer scientist, they'll just say topsort, for sure. So it is or a topological ordering of a directed graph is an ordering of the vertices such that, or we'll call it v1 dot 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 vn, such that for every edge, if I have an edge vi, vj in my set of edges, I is less than j. Or in other words, right, if I have an edge from some vertex I to some vertex j, then the first vertex comes before the second vertex in this list. Right, another way to say this is, all edges point to the right. Okay, so if I've got maybe something like this, right? This is some directed graph, and I've put the vertices in a left to right order, and all the directed edges are always pointing from something on the left to something further down to the right. Okay, so this would be, if these are course prerequisites, right, I could take the courses in this order, and by the time I got to any course, I would already have the required prerequisites for it. Okay, so I'm just going to put an example graph in here. Supposed to be a 4. No. Okay. I'll let you stare at that for a second. So, is this a DAG? Raise your hand if you think, yes, this is a DAG. Well, I can't see you if you physically raise your hand. You could like to do a little, yeah. Okay. So, a bunch of people say yes. Okay. I actually, I think I meant to draw it first so that it wasn't, but I think you're right. I think this is a DAG. I was going to draw this edge first, pointing the other way, which obviously then, right, now it's not a DAG, right, because I've got this, now I have a cycle here. Okay, so the next question is, does it have a topological ordering? So, maybe someone tell me, like, what vertex do you think should come first in topological ordering? Daniel says 1. Is that what you're saying, Daniel? Vertex 1? Okay? You put vertex 1 first, then what should come next? Y'all can go ahead and just jump in. Dan? Yeah.
I'm thinking you want to pick a vertex that only has arrows going out from it.
Okay.
And
why is that?
For your first one? Well, because if you've got a vertex that has an arrow coming into it, there's got to be something to the left of it.
Right. Yeah, that's right. So vertex 1 has some arrows coming into it, some edges coming into it. So these vertices would have to go to the left of vertex 1 in a valid topological ordering, right? So yeah, we can't put 1 first. So, okay, so then you said, Dan, you want to put a vertex first that has no incoming edges?
Maybe try 6.
Okay.
See how it works.
Let's try 6. All right, cool. Someone else, what do you want to put next?
Four.
4, okay. And 6 has an edge to 4, right? Okay. What next? You still have your hand up, Griffith, or you just set from before?
Sorry, I just forgot to click the
Oh,
button.
no worries. No worries. It's easy to forget. It makes me laugh because I'm just imagining, like, if in the physical world you put your hand up and you just kind of forgot, and you're just sitting there, like, with your hand up. It's like, oh, sorry, I forgot to put my hand in. Yeah. What should we do after 4?
I'm actually raising my hand this time.
Okay.
3 could go, I think.
Okay. That's right, 3. So 4 has an edge to 3. Okay, I'm just like putting in the edges kind of as we do this, because ultimately I want to have all the edges drawn on here, but they should all be going to the right. Okay, what next? 1, okay. So 4 has an edge to 1, and also 3 has an edge to 1. So far, so good. Now what? I've only got 2 vertices left. 5 and 2, I think. So should we do 5, 2 or 2, 5?
2, 5.
2, 5?
No, 5.
Oh, do 5. Okay. 5 and then 2 at the end? Yeah, so 4, 5, and 5 will go to 2. 1 goes to 2. Also 6 goes to 2. Okay. I think this works. Right, so that's a valid topological ordering. Is this the only one, or are there others? Is there a different order I could put the vertices in that would still work?
You do 6, 4, 5, and then 2, and then 3 and 1 will get mapped over like we're doing in the picture.
So 6, 4, 5, 2, 3, 1?
Yeah.
I think it would get messed up with 1.
Yeah, 1 has an edge to 2, so I can't put 2 before 1.
They have to be in order. Okay.
Yeah.
Switch 5 and 3.
Switch 5 and 3. That would, so 3 goes over here after 1, then 3 is going to have an edge to 1, so 3 has to come before 1.
What if you just moved 5 in between 4 and 3?
Move 5 in between 4 and 3. So kind of hold this over here like this, like that. Just gonna stick it in there. Yeah, I think that would work. Yeah, so 5 could go here, or it could go here, or it could go here. Any of those 3 places would be okay. Anyway, the point is, right, that a topological ordering may not be unique. So there could be multiple topological orderings that would work if one exists. Okay, so I've introduced two different concepts, right? The concept of a directed acyclic graph and the concept of a topological ordering. And so the question is, what's the relationship between them? So, options include there's no relationship at all, I'm just trolling you. Another option could be, right, every DAG has a topological ordering, but not necessarily vice versa. Or it could be that, if there's a topological ordering, it's definitely a DAG, but not vice versa. Or it could be an if and only if, right? Like these are kind of the same thing. So anyone have a guess?
I'll guess if and only if.
Okay. How many people vote for if and only if? Okay. Anyone want to vote that a DAG definitely has a topological ordering, but there could be other kinds of graphs that also have topological ordering? Griffith's like, nope. All right. You're right. It is an if only if. So this direction, it's nice because if we have a DAG that represents some kind of relationships where there's never a cycle, then you can always put the things in an order so that kind of respects all the relationships. And the other direction, actually, if you think about it, is probably the easier direction to understand. Like, if I can draw a graph like this so that all the edges go to the right, how could there possibly be a cycle? Right? A cycle would have to have at least one edge that comes back to the left. Right? So that direction is very easy. So the other direction really is the interesting one, right? This direction to say, if we have a DAG, then it definitely has a topological ordering. That kind of seems sensible, but it's not as obvious, and it's going to require like writing an algorithm to say how to actually find one. Or that's how we're going to do it. All right, so I'm going to erase a lot of stuff here, and then I'm going to erase this too. So theorem. A directed graph which direction I want to write this? Probably doesn't matter. Oh yeah, I'll write this way. Has a topological ordering if and only if it is a DAG. Alright, let's prove it. So this direction, as I just said, is the easy one. So this direction says if a graph has a topological ordering, then it's a DAG. That means it has no directed cycles. And the proof is, so I'll say, a graph with a topological ordering is a DAG. And the proof is, right, a graph with a topological ordering can't have any cycles because a cycle must have at least one edge pointing to the left. topological order. Right? Just to draw a little picture, like this are your edges that make a cycle. Right? Eventually, to make it a cycle, there's going to have to be an edge, at least one edge. There could be multiple edges, but at least one that's going to point back to the left. And if you wanted to make it really formal, you say, well, let's look at a cycle, look at all the vertices in the cycle. There has to be a lowest vertex in the order by the well-ordering principle or something, and then you say, well, the edge coming into that vertex has to come from something bigger to something small. All right, let's do the other direction. And we're pretty much going to spend the rest of class today doing the other direction. It's more interesting. So in the other direction, we have to say, like, given a DAG, we have to find a topological ordering for it. Well, no. A mathematician would be satisfied with saying, I have a DAG, and I'm going to prove that a topological ordering must exist. Right? We're not satisfied with that. We want to actually compute one. Right, this is given a DAG, find a topological ordering. This is just a random aside. I was reminded of this recently. I was reading something about Euclid. Euclid's Elements is this famous geometry book from ancient Greece. This guy named Euclid kind of compiled all these, propositions and theorems, etc., about geometry. But for Euclid didn't make, like, we make a big distinction between, like, theorems and constructions, right? A theorem is like proving something is true, and a construction is like how to make something. And when we teach geometry in our minds, those are kind of very different things. They weren't really that separate to Euclid. And so often you'll have, say theorem, and it says to find an inscribed triangle in a whatever. And then he just kind of like gives a construction. But also while he's giving the construction, he's like explaining why it's the correct construction. So it's a proof and a construction at the same time. And they weren't like separate things to him. That's what we're doing too, right? So we could phrase this as like, theorem, to find a topological ordering of a directed acyclic graph. And then the proof is, here's an algorithm. Now, we're going to have to pause here actually, and like kind of push this on the stack because we're going to need a lemma, and we're going to have to prove that separately. So, here's the lemma we're going to need. And actually, this goes back to, so when we were doing the example, right? I think it was Dan that suggested, like, we're going to want to put a vertex first that has no incoming edges, right? That seems pretty clear that the vertex that goes to the very beginning of the topological ordering can't have any incoming edges, because then something else, whatever's on the other end of that incoming edge, would have to be before it. So we're going to need a lemma that says a directed acyclic graph always has some vertex with no incoming edges. Okay? So any DAG, I guess I should say like a non-empty DAG. Technically, the empty graph, which has no vertices and no edges, is a DAG, but it doesn't have a vertex with no incoming edges. So any non-empty DAG has a vertex with, and using our fancy terminology, with in degree 0. It means no incoming edges. Okay, and let's prove this. We're also going to prove this by algorithm. That is, I'm going to give an explicit procedure for finding one, which if we really want to, if we're going to use this lemma and we want this to end up being an algorithm we can actually run, then this lemma had better also have, something we can run if we need to use it. So here's what we're going to do. Pick any starting vertex. And we're going to follow edges backwards until reaching a vertex within degree 0. Right, so I'm going to say a little more in a second, but right, the idea is if I'm at a vertex and it doesn't have in degree 0, then it has an incoming edge, and so I can follow that edge backwards. And I keep doing that, right? And like either I'm going to keep doing that forever, or I'm eventually going to get stuck because I've reached a vertex in degree 0. But I claim that we can't keep doing it forever. We can't continue following edges backwards forever. Why is that? And I guess actually have to be a little careful here, because I don't think we've ever actually said this. In this class, because we're like computing stuff, we're only going to consider graphs with finite sets of vertices. It's very, mathematically speaking, it's perfectly fine to talk about graphs with an infinite number of vertices or infinite number of edges. That's a perfectly reasonable thing to do. We just don't care about them in this class because it's kind of hard to write algorithms that run on graphs with infinitely many vertices. So, since there's a finite number of vertices, like, I guess it's by the pigeonhole principle. If so, by the pigeonhole principle, we would eventually visit the same vertex twice. Right, but that would make a cycle because we're always following edges backwards. And so if we ever came back to a vertex we'd been to before, like we would have made a cycle. Which would make a cycle. Okay. Right, said another way, there's not enough room in a finite graph to keep following edges backwards forever. You're either going to find start looping, or you're going to eventually get stuck somewhere where there's no more edges to follow backwards. Okay. So that's that. Any questions so far? All right, so now we're going to go back to return to our proof that any DAG has a topological ordering. Okay, so the proof is going to be by induction on the number of vertices, so we'll call that n. And I want to emphasize that right, I started out by saying we were going to prove this by giving an algorithm. Well, so a proof by induction on n is really the same as a recursive algorithm, right, that kind of keeps taking away one vertex at a time, or more than one perhaps. But. So by induction on n slash recursive algorithm. So some of you maybe have heard me talk about this before. Some of you have taken functional programming with me and know what I'm talking about, but induction and recursion are really the same thing. So a proof by induction and a recursive algorithm are in some sense exactly the same. And of course, yeah. There's also the fact that you have to keep in mind that using recursion and using a loop, like loops and recursion are equally powerful. Anything you can do with one, you can do with the other. So when we implement this algorithm, we typically don't actually use recursion. We'll use a loop, but you could think of it as you can implement it recursively as well if you want. So, okay, so in the base case, when n equals 1, right, because we're really talking about non-empty graphs. So the base case would be there's only one vertex. I don't care about the case where there's 0 vertices. Or we could include that case if we wanted and just say, obviously, if there's no vertices, then I can put all of the no vertices in a list, the empty list, which would make it a topological ordering. But so in this case, right, there is only one vertex and no edges. Hence a trivial topological ordering. Right, I just have that one vertex, no edges, so I just put that one vertex in a list by itself, and that's my topological ordering. And that's fine. Okay, so for the induction step, n is greater than 1. So we're going to say, you know, let G be a graph with, I should say, yeah, okay, I'm just going to say let G be a graph with k plus 1 vertices be a DAG. Sorry. Okay, so we're starting with a graph, a DAG, that has k plus 1 vertices, and we want to show it has a topological order. Right, but I'm not going to write it. Our induction hypothesis is that any graph with k vertices that's a DAG has a topological order. So pick a vertex with n degree 0. By the lemma. And we're going to call that vertex V. Okay, and that's going to be our starting vertex. Right now, if I remove that vertex from G, so that means I remove the vertex and I also remove any edges connected to it, I'm going to be left with a graph that has only k vertices instead of k plus 1. Also, by removing a vertex and some edges, I can't possibly create any cycles. If there weren't any cycles in the first place and I remove stuff, then the resulting graph also can't possibly have any cycles. Right? So G minus V, that is G with V and any adjacent edges removed, k vertices and is still a DAG. Okay, so we can of course now use our induction. Our induction hypothesis says if we have a DAG with k vertices, it's got a topological ordering. So by the induction hypothesis, G minus V has a topological ordering. And then adding V to the beginning of it is a valid topological ordering for G. Right, so in other words, here's my graph G. Here's some vertex V that's only got outgoing edges. And then here's like the rest of the graph G prime. And so if I make a topological ordering for G prime, right, so here's my topological ordering for G prime. Since V has only outgoing edges, I can stick V on the front here, and then it's got its edges that go in there, and that's fine. It just extends it into a topological ordering that's one bigger, and still all the edges only go to the right. So, well, let me stop there and ask if there are questions. So, what algorithm does this correspond to? Like, how do we actually do this? Right. Well, we can basically find a vertex with in degree 0, which we could do kind of using the procedure in that lemma by just kind of like starting somewhere and walking backwards until we find one. We delete it. We kind of remember that we say, okay, that's the first vertex in the order, and then we do the same thing again on what's left, right? So now, some of the vertices, like, this vertex here, for example, right? Maybe it had one incoming edge before, but now that we've deleted V and deleted that incoming edge, maybe this one now has in degree 0, and that could be the next vertex in our order, right? And we just keep doing that, picking another vertex with in degree 0, deleting it and all its outgoing edges, and we just repeat until we're done with everything, and that will give us a topological ordering. So, how long does that take? So the lemma part, where we start somewhere in the graph and we kind of follow edges backwards until we get to something with in degree 0, that's going to take, in the worst case, we might have to like we might pick poorly and then have to travel through like all the vertices backwards until we finally reach one with in degree 0. So that could take O of V time in the worst case. And then, of course, we're going to iterate that V times, once for every vertex. We're going to delete that vertex. I guess there's maybe a plus E in there, but it doesn't really matter, because so this is O of V squared. So finding an in degree 0 vertex takes O of V, and we do it V times. Oops. That says repeat. Okay, but we can do better. So this is kind of the easiest way to prove it, but it's not actually the most efficient way to implement this. So we can be a little bit more clever and get a faster implementation. So if you think about it, right, let's say I had a graph that looked like this. Right, and let's say, I say, okay, I want to find a vertex with in degree 0, so I'm going to start here randomly. I follow all these edges backwards. I finally find this one. So then I choose that one, and I delete it. Now I need to do the same thing again. And I say, okay, now I'm going to randomly pick a vertex. Let's start here. Right, and I go follow them all backwards. I delete this one. And I start here again. Right, every time I'm starting here and having to trace them all backwards, which is really silly because I've just done that. Right, like every single time I'm retracing my steps the exact same way. So intuitively, it's the part about finding a vertex with in degree 0 that takes too long. Doing that in O of V time seems like a waste because we're going to be probably redoing a bunch of work every single time that we're finding one. So it turns out with a little bit of clever bookkeeping, that part we can bring down to constant time. So let's see, how much time do we have? I'm just gonna, okay, yeah. So I'm gonna write up here and talk through kind of a hand-wavy outline of what we need to do, what we need to keep track of, and to make this constant time. However, I have a nicely written up version of like some pseudocode that I'm going to send out. So hopefully you'll get the general idea here, and then you can look at the pseudocode and study that in more detail. So so we want to finding in degree 0 vertices. In O1. So we want to maintain, or the big idea is to maintain some kind of a queue or list or whatever of vertices with in degree 0. It's funny, it actually doesn't really matter what data structure you use. You could use a queue, a list, a stack, I don't care, as long as you can add stuff and remove it in constant time. Like if you can add something in constant time and just remove something, it doesn't even matter which one, you just get one of them in constant time. I usually use a queue, but it doesn't matter. I mean, a different choice of data structure will mean you'll get a different topological sort out, but you'll always get a valid one. And we want to be able to, so if we have these, right, we can just like pull one off in constant time and just say, give me the next one that has in degree 0. The trick is, how do we maintain it? How do we make sure that when stuff needs to get added to it, we can add it quickly? So here's how we do it. We keep track of the in degree of every vertex. Right, so you have some kind of dictionary that maps vertices to a number, which is their in degree. And it's not hard to see how to, like, before the whole algorithm, you just go through the whole graph, and for every edge, you increment the in degree of the vertex at the end of the edge. Right, so you can do that in, just however many edges there are, you go through the edges, you build that. And then you can, if there's any, after you build that, if there's any that had in degree 0, then you throw them in the queue or whatever to start. So keep track of the in degree of every vertex, so we'll build it a dictionary in, theta e time first, and then put any vertices with in degree 0 in the queue. Okay, and that takes like theta v time to just look, go through all the vertices, look at what their in degree is, and throw any with 0 in the queue. And then, right, each time through the loop, and when I say the loop, I mean like, the loop where you pick a vertex with in degree 0 and you delete it and put that on your top sort. Look at all outgoing edges from the deleted vertex. And right, so the point is, when I delete a vertex, I'm deleting all the edges going out of it too. So I need to decrement the in degrees of all those neighbor vertices, right? Because they now have one less edge coming through. And decrement I'll say neighbor in degrees. Okay, and I don't have space to write it, but as you're doing that, when you decrement each in degree, you notice, you say, oh, did I just decrement it and did it just become 0? If it was 1 and I just decremented it to 0, then I'm going to throw it in the queue right away. I'll just say add any that becomes 0, any becoming 0 to the queue. Okay, and that's it. So if you do that, so this stuff takes this takes theta of e, this takes theta of v. That's all happening once at the beginning, and then this stuff we're looking at every edge once, and we're doing a loop for every vertex. We're looking at every edge once total, right? So the whole thing takes just theta of v plus e. And if there's not too many edges, then that's much better than v squared, right? So if there's a lot of edges, then v plus e is just v squared anyway. But if it's a sparser graph than that, it does much better.